Welcome back to the small break. Now we have Andrea Pesare that will talk, that actually will hold a small course about reinforcement learning and optimal control. So I give to you, Andrea Pesare.
Hi everyone, and thank you to the organizers for this opportunity and for this beautiful location. And today I will deal a bit with reinforcement learning and optimal control and their similarities and differences. This is the outline of the mini course. After a general introduction, I will introduce the optimal control problem and the dynamic programming approach. Later, I will describe the framework of Markov decision processes, which is the ideal framework for reinforcement learning. And so we will pass to reinforcement learning, model-free and model-based methods. And finally, I will present what I'm working on with my advisor and my colleagues. It is an optimal control framework with average cost, able to describe some reinforcement learning methods. Okay, so our aim is to control an environment in order to achieve a certain goal. For instance, we need to drive a car in order to steer it towards a certain target, and we can control it through the wheel or the accelerator pedal. So these are the controls. And yes, we can choose whatever control, but we need to reach our goal. And for instance, reach a target in a minimum time. Another example is a chess game. So we need to choose actions or moves in order to win the game. So these are all sequential decision problems where we have to take some decisions and in a certain optimal way. These two different fields, optimal control and reinforcement learning, in reality are very close to each other. And I listed here some small differences. For instance, the optimal control has been studied in both continuous and discrete setting, while reinforcement learning mostly discrete setting. Then optimal control exists deterministic or stochastic versions, and reinforcement learning mostly stochastic, but of course also includes the deterministic part. And the big difference is that optimal control is based on the model, so we know how the environment reacts, we know the dynamical system, whereas reinforcement learning uses data to control the system. So experience and direct interaction with the system. Okay, let's begin with the problem formulation for optimal control. We have the state equation in discrete time, which is a difference equation. So the next state, xk plus 1, depends on the current state, xk, and on a control variable, uk, which the agent can choose. Xk lies in Rn, in a state space X. uk lies in a control space. And we can see that given an initial state, x null, and a control sequence, the whole trajectory is uniquely determined. We are still in the deterministic setting, so we have a unique trajectory. This allows us to define a cost functional. A cost functional which depends on, I don't know if you can see the pointer, but depends on the control. And is actually a summation of all time steps of a cost function L, which depends on the current state and current control. And our goal is to minimize the whole cost functional over all possible control sequences. What is gamma? It is a discount factor. It has an economic interpretation of actualize a certain amount of money. For instance, in 10 years, 100 euros in 10 years now are worth like 80 euros. So this is its meaning, but also as a mathematical reason. In fact, gamma assures that the summation is finite whenever L is finite as well. So the goal is to find an optimal control. That is, among all possible control sequences, find the one which minimizes the cost functional. Okay? What is the time horizon? Is this capital T in the summation. Sorry. Okay, this capital T, and this can take different values. In finite horizon problem, it is a fixed finite number. In infinite horizon problem, it is infinite. And in episodic problems, it is a finite stopping time. For instance, in a chess game, the game ends whenever the king has been eaten. Okay? We have two kinds of controls: open loop and feedback controls. The difference is that the first one is a function of time, so I can tell you at time t what is the control, and feedback control is that depends can depend on time, but depends on the current state. So depends on the state and time. If it depends only on the state, it is called a stationary policy, and we define a function mu from the state space to the control space as a policy. We can write the cost functional also for policy. So here there is a typo. J of mu is the summation, the cost functional where the control is actually not uk but mu of xk. So what is the big difference is that in case of external disturbances or model errors, there is no way to correct an open loop control, whereas feedback control is more stable, more robust, and can adapt itself to the current state. So in case of disturbances, it is more stable and can deal with stochasticity. And finally, there are two main historical approaches to optimal control theory. The first one is Pontryagin maximum principle. This was developed by the Russian school in the Soviet Union during the Cold War, and led by Pontryagin, and it's based on these necessary conditions, and then you can solve some boundary value problems. Okay, and then dynamic programming, which was developed by Richard Bellman in the same years, in the 50s, and this was the American school. So during the Cold War, two different schools developed two different theories for the same problem. And so Pontryagin maximum principle can give an open loop optimal control, while dynamic programming provides optimal feedback control. This is why reinforcement learning uses dynamic programming. In fact, it deals mostly with stochastic systems. Okay, let's deal now with dynamic programming. It was proposed by Bellman in the 1950s, and the idea is to consider a family of problems in which the initial state and time is changing, and analyze the relationship between these problems. And this is the famous principle of optimality by Bellman, an optimal policy has the property that whatever the initial state, the initial decisions are, the remaining decisions must constitute an optimal policy with regard to the state resulting from the first decisions. What does it mean? That if I take, say, 10 actions, then the remaining, in an optimal way, then the remaining action will be optimal for the subproblems, for the subproblem where I start from state x10 and I want to optimize the remaining cost functional. And later we will see some concrete examples. And this is a general approach, dynamic programming, for several sequential decision-making problems, but the procedure is almost the same, and I sketched it. We can define at the beginning the value function, then the value function solves this principle of optimality, so we can state it mathematically. Then we derive the Bellman equation, which is a functional relation satisfied by the value function. We solve the Bellman equation, so we find this value function, and then we can build an optimal feedback control using the value function. Okay, let us do these steps in an example, which is the infinite horizon problem. So the assumption we make is that both the state space X and the control space U are finite, have a finite number of elements. This allows us to save all the values in tables, and this is good in numerically. This is again the state equation, the cost functional with respect to a policy. And we define the value function as the minimum cost starting from x null. So over all possible policies or control sequences, we would like to know the minimum cost that I can achieve. The principle of optimality can be stated in the following way. The value function, which is the minimum over all of the summation over all time steps up to infinity, can be also computed as the minimum over a finite number of control, so n, small n controls, and then we will arrive to a certain state xn, and from that point on we will act optimally. In fact, Vxn is defined as the optimal policy starting from xn. From the principle of optimality, we can derive the Bellman equation, which is a one-step formula, and says that the value function satisfies this relation. The value in x is the minimum over all controls of the current state, cost L of xu, plus gamma, which is a discount for one step, times the value function in the next state. And the next state is f of x and u. Okay, if you remember the dynamics, xk plus 1 is f of xk and uk. So this is a one-step formula, and if we manage to solve it, we can get the value function. How to solve the Bellman equation? There are two main algorithms. The first one is value iteration, which iterates through a fixed point method the equation. So the operator on the right hand side is called the Bellman operator, and it is a contraction. So when gamma is smaller than 1, so we can iterate, and the fixed point method converges to the solution of the equation. It is called value iteration because it iterates over value functions, and so it generates a sequence of approximations of the value function, and it is proven to converge. Okay. The other algorithm is policy iteration, and the idea is to alternate two steps, which are policy evaluation and policy improvement. And policy iteration iterates over policies, so it builds a sequence of policies, mu k, and precisely in the policy evaluation step, we have a policy mu, and we compute the cost of the trajectories under policy mu. So we compute that infinite summation. How we compute it? We can prove that this value v mu, defined as a cost j x null under policy mu, solve this linear version of the Bellman equation. So this is a linear system, and we can solve it how we want. For instance, directly or iteratively. In policy evaluation, we usually iterate, so we solve a linear system through an iterative method. Then, so if we solve this equation, we will get this value function v mu. So now the terminology varies from field to field, from optimal control to reinforcement learning. So we can also indicate this function v mu as a value function for a policy mu, and the previous one as the optimal value function. Okay, there is this bit difference. After we evaluate the policy, we can improve the policy. We can build a new policy, mu prime. So we started from mu, we computed the cost under policy mu, and now we can improve mu, getting a new policy mu prime. And we use this formula. I don't go into the detail, but there is a theorem which says that the new policy is better than the previous one. What does it mean? The cost of the new policy is less or equal than the previous cost for each state. Okay, so we are going monotonically, okay, decreasing. This is a sketch from the book of Sapienza and Barto. We start from mu 0, we evaluate and we compute the cost v mu 0, and then we improve the policy, we get mu 1, we evaluate it, and finally we converge to the optimal policy and the optimal value function. Okay, so we saw the two main algorithms of DP, and they are simple, also simple to implement. They work, but they have weaknesses. The first of all is that the computational cost is high, especially when the state space is large. And there is the so-called curse of dimensionality, which maybe you know. This means that whenever the dimension of the space increases, then the cost increases exponentially with respect to the dimension. And actually this term was coined by Bellman precisely for dynamic programming problem. So for most problems, we cannot compute dynamic programming precisely, exactly, and so we will see some approximate dynamic programming algorithms. And another weakness is that dynamic programming requires to have a full knowledge of the system, so to know the dynamics function f and the cost function L. There are other methods for optimal control problems. I just listed them. Pontryagin maximum principle. We solve a boundary value problem, which are some necessary conditions for the optimal control. Model predictive control, which solves not an infinite horizon problem, but smaller finite horizon problems. This is called also receding time horizon. Okay, I don't go into the details. Direct methods, which optimizes directly over control sequences. So we discretize, and it is an optimization problem. So there are several methods for optimal control. We just saw briefly one, which is dynamic programming, but now we go ahead with Markov decision processes. And we start from a stochastic version of the previous system. So the system is the same, the dynamical system is the same. Xk plus 1 depends on xk, on uk, and now on a random disturbance, omega k. What is this disturbance? Well, it is a stochastic process which incorporates all the stochasticity of the system. There are tons of ways to define it, and once we define this omega, we can define a cost functional as the expected cost functional, as the expectation of this summation. Okay, the expectation is with respect to omega, so to the stochastic process. We call this calligraphic P the set of all policies, and these are deterministic policy. We can also consider stochastic policies. Okay, for now we use deterministic policy, and the goal is again to minimize the cost function. Among all possible choices of omega, we consider Markov decision processes for which omega is Markovian process. And in particular, there exists a function small p such that the distribution of xk plus 1 given the current state xk and uk is given by this function p. Okay? And more precisely, the probability that xk plus 1 equals x prime, given that xk equals x and uk equals u, is p of x prime given x and u. Okay? So for who of you know Markov chains, this is a generalization of Markov chains. This is also called controlled Markov chains. And it has two more variables, the control or action. In reinforcement learning they call it an action, uk, and the cost or reward, rk, which is exactly L of xk, uk, and omega k. So why cost or reward? Sometimes we need to minimize the cost functional. Sometimes we want to maximize a payoff functional or a reward functional. But they are two equivalent problems, so I will jump into the two terminologies. The distribution of Rk is also Markovian, depends only on the current state and action, and is described by this small q. The history of the process is a sequence of the whole trajectory, state, action, and reward, up to, here is up to a finite time k. And the Markov property can be written as following: the probability, the distribution of xk plus 1 given xk and uk equals the distribution of xk plus 1 given the whole history of the process. This is the Markov property. So among all stochastic systems, we are considering these Markovian systems. we can define now, we define again all things but with different notations, which are the notation of reinforcement learning. And the return is defined as the cumulative sum of rewards. So the current reward Rk, then the next reward Rk plus 1 but discounted by gamma, and then so on up to the final time. And the loss functional is the expected cumulative cost or expected return. Okay, given that I start from x null equals x. Okay, why we consider Markov decision processes, and why most of RL algorithms are set in Markov decision processes? I don't know, but the thing is that the two main references for RL are set in this framework, and so I try to answer. So this is a perfect framework for a sequential decision-making problem. It is simple and easy to work with, even mathematically, and it is rather general. There is a discrete space or a continuous space variant, stochastic, but also includes the deterministic case. So this is the fact. RL is set in Mdps. So, and the curiosity is that Mdps were born as a stochastic control framework. So introduced by Bellman again as the stochastic variant of the discrete problem, which I presented before. So MDPs are control problems, but reinforcement learning solves them in a different way. We can briefly discuss dynamic programming from MDPs. We consider finite MDPs, which means finite state space and control space. The value function of a policy mu is the expected return starting from a state x. This is called also the state value function because it depends only on the state. And the optimal state value function of the MDP is the minimum over all policy. So the minimum cost that I can achieve. Okay, the same definitions as before. There are two main tasks. The first is prediction or evaluation task. That is, given a policy mu, compute the cost of the policy. And the control task, find the optimal value function p star and or an optimal policy mu star. Important note, dynamic programming assumes complete knowledge of the MDP. What does it mean? We know small p, so the distribution of the next state, and we know small q, which is the distribution of the reward. We can derive a value function, a Bellman equation for a policy by these simple steps. So the reward, the return Rk is the summation of all time steps of the reward. So we can write it as the reward plus gamma times the optimal return starting from the next state. And so the Bellman equation becomes this one. This is the Bellman equation for MDPs. And since we are in the finite assumption, we can compute, as in a Markov chain, we can compute this expectation as a sum over all possible actions and over all possible actions of, I don't know if this is correct, but we can compute it as a sum of all possible next states of the value function in the next state. Okay, we can define an analogous action value function, which depends on the current state and action. So what does it mean? We start from x, we take action u, and then we proceed using policy mu, and this definition is given by this formula. And is defined as q mu depending on x and u. This also satisfies the Bellman equation, but we don't need it. Why we define this? It is useful. For some algorithms, which we will see later. The policy evaluation, which we saw before for the discrete deterministic case, is the same. So it is an iteration. The Bellman equation for a policy is linear, but now we have an expectation. So it is more difficult to compute. It has an higher cost, but is very simple. So a linear system, and we can use an iterative method. So we use policy evaluation given a policy mu to compute the cost of the policy. And analogous method for q mu, given a policy, you can compute the action value function. The Bellman optimality equations are the Bellman equation for the optimal value function, V star. V star is defined as the minimum over all policies, so the minimum cost I can achieve, and the one I want actually to compute. And the Bellman equation for V star, the difference is that it is nonlinear because there is this minimum operator which makes it nonlinear. But anyway, this is a contraction, so we can use a fixed point method. So the value iteration method is the same as before. The optimal action value function is defined as the minimum of the action value function with respect to all policies. So we saw the policy evaluation, and then there is the step of policy improvement. So take a deterministic policy mu. At a given state x, would it be better to do an action u instead of mu of x? We want to improve the policy, so we ask if there is a better action at state x. If yes, we can improve the policy. And there is this formula. And again, a theorem, policy improvement theorem, which says that the new policy is better than the previous one. That is, the cost of the new policy is less or equal than the previous cost. And this is also important, that equality holds if and only if both policies are optimal. Why is this important? We are iterating, so this gives a stopping criterion. Whenever two subsequent policies have the same value function, this means that we have achieved convergence. The policy iteration algorithm alternates policy evaluation and policy improvement as before. So we start from mu0, we evaluate it, and we get v mu0. We improve the policy and we get a new policy, and so on. So deterministic case, stochastic case, but the algorithm is the same. And we have also we only have the expectation in addition. Value iteration is a fixed point method on the optimality Bellman equation. And now, so until now we talked about dynamic programming for Mdps, but it was still optimal control. And now we pass to reinforcement learning. there are different names for the same thing. The first one is reinforcement learning, the most famous, and this comes from the reinforcement phenomenon in behavioral psychology. This is when a child behaves well and I give him sweets, and so he will behave well in the future. This is the reinforcement phenomenon. And at the same time, an algorithm interacts with an environment, and whenever an action produces a good return, then the value of this action is increased by the algorithm. Another term, and this is interesting, is approximate dynamic programming. So reinforcement learning can be seen as approximate methods to solve the dynamic programming equations, which are Bellman equations. Okay, we cannot solve them exactly when the state space is large, but we can use approximate methods. And another term is neurodynamic programming, which is actually the title of the book by Bertsekas and Tsitsiklis. Why neuro? Neuro stands for neural networks, but also all function approximators. So it should be approximate dynamic programming using neural networks or function approximators. This should be the whole title. And the definition of reinforcement learning on this book, the methods of this book allow systems to learn how to make good decisions by observing their own behavior through simulation with the environment, and use built-in mechanisms for improving their actions through our reinforcement mechanisms. Okay, I interact with the environment, I see which actions are good, which are bad, and I learn how to behave. Why reinforcement learning? So when is it useful to use reinforcement learning? When a complete model of the system is available, but the state space is too large. And we already discussed about this. This is called the coarser dimensionality phenomenon. How we can deal with it? Dynamic programming plus an approximation in the value space. For instance, we consider a subclass of value functions depending on a parameter, and we iterate over the parameter instead of over the whole states. Or we can use RL when a complete model of the system is not available. So we are dealing with an unknown environment, and we learn how the environment reacts to our action during the process. Sometimes we have an external simulator, sometimes we don't. So we can work offline or online, but these are two main cases: when the state space is large, or when we don't have the complete model of the system. We can distinguish between two classes of methods. Model-free and model-based reinforcement learning. Model-free methods use no model. They learn a policy or a value function directly from experience. They need low memory and computational cost, but learning may be slower. Model-based reinforcement learning learn or estimate a model. So at the beginning they learn a model, and then they use the model to find an optimal policy. For instance, using DP algorithms. They are sample efficient, but they need a higher computational cost. And the main disadvantage of model-based is the so-called model bias. What does it mean? If my model is not accurate, the policy which I find will not be accurate, and will be accurate up to the accuracy of the model. And so this leads to suboptimal policies and can be a huge problem. Okay, let's discuss about some simple and classical model-free algorithms. They learn directly from episodes of experience. What is an episode? Is a sequence, the whole history of the process. So we have state, control, action, reward in sequence. X null, U null, R null, X1, U null, U1, R1, and so on, up to the final time t, which is usually an episodic problem, so t is a stopping time. Again, the prediction task, given an episode E or a sequence of episodes, we estimate the value of a certain policy mu, where mu is the policy we are following during the episodes. Okay, what does it mean? UI is defined, UI in here, UI in the episodes is defined as mu of the current state xi. The control task, given an episode or a sequence of episodes, build an optimal policy. Two classes of algorithms we will see today. Monte Carlo methods, which there are two variants, first visit or every visit Monte Carlo. Temporal difference learning, then TD0, SARSA, and Q-learning. Let's start with Monte Carlo. They learn from complete episodes, so we need to end the episodes in order to use Monte Carlo. The idea, as other Monte Carlo approaches, is to estimate the expectation of a random variable with the empirical mean. For instance, the expectation of x, of capital X, is approximated by the empirical mean when xi is distributed as x. And the simplest Monte Carlo algorithm for evaluation is the following. Recall that the definition of value function for a policy mu. So the expected return starting from a state x and acting following a policy mu. How we can estimate it? We start from state x several times. We observe the final return, so the cumulative sum of the rewards, and then we average all the results over all simulations. This is what Monte Carlo does. There are two variants. First visit, for each episode, we consider only the first time that I reach state x. And see, starting from that state, observe the final return. But it could happen that in a single episode, we pass into state x several times. For instance, x1 and x10, we go in the same step, in the same state. Then we can use these as two separate simulations and have more data. Okay, so there are two different methods with some properties. The first one is unbiased. This means that the expected value is the true value function. And the second one is biased but consistent. So in the limit, it will converge to the right thing. The second one is faster because it has more data. This was Monte Carlo for the evaluation task. Given a policy, we compute the cost of the policy. Monte Carlo for control, and this is the analogous of policy iteration algorithm. We use policy evaluation on the state action value, and then we use an epsilon greedy policy improvement. So now maybe it's not clear why we use Q. Okay, let's see if I can explain better. Okay, here the new policy in policy improvement in standard dynamic programming for MDP is defined as the minimum of Q mu. And Q mu, so it's the minimum of this expectation here. The expectation can be computed if we know the distributions P and Q, small p and small q. Okay, so in general dynamic programming, we can compute the expectation directly. In reinforcement learning, we don't have the distribution of the process, so we cannot do whatever we want. We need to use the things that we have, and in particular, we can compute Q with policy evaluation, and then use Q in the policy improvement. We don't need the distribution in this case, because the policy improvement is the minimum, or yes, here is maximum, is the minimum of the Q function. Okay, it's just a trick that we use. What is the main issue? That the Q function depends both on the state and on the control, on the state and on the action. So there are many values that I need to estimate. The value function depends only on the state. So if I have 100 states, I need to estimate 100 values through Monte Carlo simulations. Q value function depends on 100 states times 100 actions. So it's 10,000. And we need also to explore the state space. In fact, if I use a deterministic policy, when I reach a state X, I will always do the same action U. I will not change actions. So this is why we add some random moves. With probability epsilon, we move randomly. So from state X, with probability 1 minus epsilon, we do the one which we think is the best choice, is the best action. And with probability epsilon, we move randomly. In this way, we can explore all the possible actions, in the limit, of course. And we can prove that if we alternate these two steps, policy evaluation for the Q and policy improvement in this epsilon greedy way, then we converge to the optimal policy. This was Monte Carlo model-free reinforcement learning. Temporal difference can learn instead from incomplete episodes. Monte Carlo needs to finish the episode to observe the final return and use it to estimate the value function. Instead, temporal difference works online. So at each step, it updates the estimate. And it is not necessary that the episode ends, and it is not necessary that the problem is episodic. It could also be infinite horizon. We can use TD learning. The idea is to start from the empirical mean of Monte Carlo, but write it in a different way as an incremental mean. That is, the expectation of X we estimate it with the empirical mean xn. This is the sum of all xi divided by n. This is xn plus the previous ones. And finally, we can write it as the previous average plus 1 over n of this difference, so temporal difference. Okay, and this 1 over n, it is not important that it's precise because it will change over time, 1 over n, but we fix it, we say this is alpha, and so we have a general update formula. The value function of time x updated is the previous estimate plus a coefficient alpha times a new value, which I observed, minus the previous value. Okay? So we have an update formula, which is general, and we can also write Monte Carlo update in this way. In fact, Monte Carlo update, we have alpha n equals 1 over n, and n is the number of the visits, the number of times I've already been in that state, and rk is the observed return at the end of the episode, and this is a new estimate for my value function, so I add my new estimate in this way. Instead, temporal difference doesn't use the actual observed return, but an estimate of the return. How? It uses, this is similar to the Bellman equation, so it is an idea from dynamic programming. It uses the current reward, rk, plus gamma times the value function in the next state. So rk plus gamma v xk plus 1 is an estimation of the return. And we have a new formula, and the advantage of this formula is that we can use it online. At each step we can update the formula, and this allows to use incomplete episodes. Temporal difference prediction, thus we can describe it this way. We get an episode E and an initial value function, and then for each state we update the estimate value function of this state where I am. So V, the value function, the previous value function, plus a factor alpha, which multiplies an estimate, a new estimate of the value function minus the previous one. And this can also be written as this. For me, it's clearer. So we, instead of V of xk, we substitute 1 minus alpha times the previous estimate plus alpha and the new estimate. So we are doing a weighted average of two different values. Alpha is called the learning rate. And okay, and V is converging to V mu. So there are some results, theoretical results, which I am not present. Okay, SARSA is one version of TD learning for the control task, and in particular, it uses a policy evaluation. Again, on the Q value function. So this algorithm which I showed you, not on V but on Q, with the same update. So alpha, this is the new estimate now, rk plus gamma Q in the next state and action. And again, an epsilon greedy policy improvement. This is needed to explore all the possible actions. This is called on-policy TD control. This is an on-policy algorithm. On-policy means that I am estimating the value function of the policy I am using to choose actions. In off-policy methods, we use a certain policy, but we estimate the value function of an optimal policy, of another policy. And this is Q-learning, so it uses policy evaluation in a different way. Here it puts the minimum or maximum of Q, and they always the same epsilon greedy epsilon. Okay? So last slides, and then we can have a break. On policy and off policy, Monte Carlo control and Sarsa are said on policy. On policy methods attempt to evaluate or improve the policy that is used to make decisions, while Q-learning is said off policy. And these methods evaluate or improve a policy different from the one which is used to generate the data. In these last slides, I don't know if you can see, but so it's not mine, I took it from another course, but it compares the three approaches: Monte Carlo, temporal difference, and dynamic programming. So Monte Carlo, to update the value function at the state S, it observes all the path toward the end of the episode. And then use this incremental, we can write it as an incremental update. Temporal difference only look to the next state, and then approximate the value function as the current reward plus the value function in the next state. Dynamic programming instead looks into all possible next states and take the expectation. Okay. So in order to use dynamic programming, I need to know the probability with whom I go into each state. Instead, for Monte Carlo temporal difference, I just need simulations. I approximate the distribution using simulations. Okay, last slide. Is reinforcement learning optimal control without knowing the model? Well, actually, already in the 50s, there was this variant of adaptive control. Adaptive control is the study of controllers which must adapt or adjust themselves to handle unknown model uncertainties. So, adaptive control is an optimal control problem where the controller needs to adapt himself online. And in the typical setting, the system dynamics depends on parameters. And we either don't know the parameter of the system, so the system is unknown, or the parameter is changing over time. And we can see some similarities. And in fact, there is this famous paper by Sutton, Barto, and Williams. The title is Reinforcement Learning is Direct Adaptive Optimal Control. There is a clear identification. I say that they refer to model-free reinforcement learning in that case. So reinforcement learning can be seen as this adaptive control in which I don't know the model of the environment, or the model is changing and I need to adapt my controller. However, we will see in the next slides that model-based, no, we will not see this, but model-based reinforcement learning is similar to indirect adaptive optimal control. Already in adaptive control, there were two classes of models, direct and indirect, which can be thought of model-free and model-based methods. Now we have a break, and we go on later. Thank you.
Thank you for the first part part of the mini course, and I think actually we can have a break, as you said, 5, 10, something like that. How many time do you require to complete your?
No idea.
Okay. Because I believe 5 minutes or something like that. It's fine. So anyway, by any means, anyone has any question, is the good time to do that now. And so, anyone has a question? Zambon.
I have one. Could you please go back to slide 15, I think, something like that. Yeah. Okay, so we have that both the dynamics and the reward are like deterministic functions of omega k, right?
Yeah.
So the source of stochasticity is the same for both, so they're not like independent.
They
or they could be independent or not.
They could be independent.
Okay.
This is just a notation to make a parallel with discrete setting. They could be independent.
Okay, but is it like an hypothesis that you usually do, the independence of the reward and the dynamics, or doesn't matter?
I think it doesn't matter. Sometimes they write not in this form, but they write the probability of xk plus 1 equals x prime, comma, rk equals r,
Okay.
given the current state and action. But it's rather general, so it could be dependent.
Okay.
So they have how do you say?
So you can use the joint distribution.
Yeah, it's a joint distribution, but it could be either dependent or independent.
Thanks.
Okay, perfect. Anyone? Yanni?
One thing, you said that Monte Carlo approximation needs the entire history, entire data, and cannot be performed online. Yes. But I didn't catch why, because of the to do it each time.
No,
in order to have the mean, the error.
Okay, so Monte Carlo, I don't know if you can read this, but the updates in Monte Carlo uses here a new estimate of the value function is the actual observed return. But the return is the sum of all rewards up to the final time.
Okay. And another one, with dynamic programming, you just look at multiple models and then you average at each time the tree.
Yes.
Okay. If you take a branch, you just are choosing one model, or
Okay. The value function is defined as the expectation. So it considers all possible values or all possible trajectories. Okay, because this is a stochastic process. So
with in different trajectory.
yeah.
Okay.
So,
Thank you.
any other questions? Okay,
have one more.
You're a curious guy.
So, do you know if anybody ever deals with also open loop strategies, open loop controls in reinforcement learning?
I don't know this, but since most settings are stochastic, they usually prefer feedback controls.
Okay.
But I don't know.
And in feedback control, you could also do like a stochastic feedback control, right?
Right. Yes. In stochastic optimal control, the control is a stochastic process. There is a whole theory with diffusion equations, more general than Mdps.
Okay.
Well, the stochastic control actually, it would be nice if it actually converges towards something like Dirac's delta at some point, because they are the optimal. And this one is what are you aiming for? Okay, so any other questions? We are resuming with the mini course by Andrea Pesare. And without any further ado, go ahead.
Okay. We keep. Sit on. We keep going. No.
Yeah, yeah.
It's not working.
Ma lì,
E poi anche un tastino lì. L'hanno fatto ieri.
dove che si schiacciava?
Questo non era
L'ho sempre fatto con. Prova.
un a caso.
Ah, ok, se ci metti te.
In qualche maniera risolviamo.
Prova.
Così c'è un tasto da pigiare.
Dice qualcosa da
C'è
schiacciare.
un tasto da pigiare.
Sì. Ok. Great. We keep going, so we looked into model-free reinforcement learning for Mdps, and now we go towards model-based reinforcement learning, or MBRL. And a model-based method consists in 2 steps. First of all, we learn a model, and then we use the model to solve the control problem. The properties are that it is sample efficient, higher computational costs, but there is this model bias problem. Okay, now we look to a subclass, which is model-based reinforcement learning for deterministic systems. So the dynamics is basically a function f. We have a difference equation, the cost functional. The difference with optimal control is that here the dynamics f is unknown. So a model-based algorithm will first learn f from experience using supervised learning, or this is a regression task, and then use the estimated models to solve the control problem. The problem is that if the model is not accurate, I will produce a suboptimal policy.
Sente? No.
For me, it's not.
Professional microfono?
No.
Okay, so I think we can go with this.
Okay, what is the idea of probabilistic model-based reinforcement learning? Is to use a probabilistic model in order to reduce model bias. So we make the model uncertainty explicit in the model, so we don't have a function f which approximate the dynamics, but we have several possibilities. We have some uncertainty in my model, and we incorporate model uncertainty into long-term planning. So we consider averages over possible dynamics. Okay, and this is the setting. So the function f now is latent. We don't know it, and we can formalize a probabilistic model as a probability distribution pi on a space of functions. Space of functions, a subset of bounded and continuous functions. Okay, whatever. But the idea is that a probabilistic model, we read it as a probability distributions on dynamics. And pi describes our knowledge on the true dynamics, f. Some examples of pi. In the simplest case, pi can be written as a weighted sum of Dirac deltas. For instance, we know that there are 10 possible dynamics, and then we give to each of them a weight, a probability to be the true dynamics. Or, more complex, we can use Gaussian processes. What are Gaussian processes? We can see them for each couple x and u. There is a random variable, a Gaussian random variable, and then for each 2 couples there is a covariance. So it is a generalization of a Gaussian random variable. But you can think of many other examples of probability distributions on space of functions. Here we present some, I listed some famous methods which are popular today, and the two steps are these two. So build a model, how we build a probabilistic model using a Gaussian process, or a Bayesian version of a neural networks. These are called deep B and N. And then we use the model to construct a controller via a policy search algorithm or a model predictive control. And in particular, there is the first algorithm was Pilko in 2011 that uses Gaussian processes and then policy search. Then the same authors proposed a neural network version of Pilko, which uses Bayesian neural networks and then policy search. Then Kante and Dijsselhout proposed this Gaussian processes model predictive control pair. And these other two are probably still the state of the art, and they use ensembles of Bayesian neural networks plus either model predictive control or policy search. So using these tools, you can they tried all possible combinations, and they constructed several methods. And the issue of these methods is that they provide excellent performance for some problems, but they have no theoretical guarantee of convergence for a general problem. And what we try to do is to provide this convergent guarantee. So we developed a framework, an optimal control framework with an average cost to describe what is happening when you use a probabilistic model like those before. This is the continuous time version of an optimal control problem, where the dynamics is now an ODE, a controlled ODE system. So x dot depends on equals f of x of t and u of t. X is always the state, u of t is the control, and the function f is continuous and assumed to be Lipschitz in the state variable. We use measurable control, so a control is a measurable function from 0 infinity to u, and there exists, for a given control, there exists a unique trajectory by standard ODE theory. And so we can define the cost functional as an integral instead of a summation from 0 to infinity of a cost function times a discounted factor. And the goal is to find an optimal control. Now the control is a function, so it's an infinite dimensional problem. If we know f, if we know the dynamics, there are several numerical methods to solve optimal control problems. There is the dynamic programming variant of in continuous time, Pontryagin maximum principle, model predictive control, direct methods, and others. But the fact is that now we don't know f, so we are assuming the setting typical of reinforcement learning. But we know that f lies in a certain subset of the bounded and continuous functions. We call x the space of possible dynamics. And we say that our belief of f, what we know about f, can be described by a probability distribution pi on the space x. So if we observe that from state x, acting with an action u, you will go in a certain direction, then our probability distribution will be certain in that point. But around, we don't have other information, so there will be some uncertainty. Again, these are some examples of probability distribution. And think of Gaussian processes because some of the model-based reinforcement learning algorithms which are famous and they use Gaussian processes. So we studied this optimal control problem with uncertain dynamics, where the dynamics is not just one, but there are infinitely many possible dynamics. And we define the cost functional as the expectation with respect to pi as the average cost over all possible dynamics. So for each dynamics, we will have a certain trajectory, and then we average the cost of all possible trajectories. The important thing is that the control is unique. So we choose a single control for all trajectories. We don't know which one is the true one, and we want to do well on average. This is an example of a optimal multi-trajectory. Here we have 3 possible dynamical systems, and we don't know which one. We gave them probability 1/3 to each possible dynamics. We don't know which one is the true one, so we try to do well on everyone, on every dynamics on average. The initial point is the same, and you see that, let's say on average, the dynamics is going toward the origin, which is the target of the problem. So we have 2 problems which we compare. On the left side, we have a classical optimal control problem with a single dynamics f and an integral as optimal as cost functional. And on the right hand side, we have infinitely many possible trajectories, and as a cost functional, we average the cost of each trajectory. The value function and the optimal control is defined as in the discrete case. So the minimum or the inf over all of the class of admissible controls, so measurable functions of the cost functional. The optimal control is, if exists, the minimum, the arg mean of the cost functional, and here we write v pi and u pi star. So the notation pi means that we fixed a probability distribution pi. So what about the convergence of probabilistic methods? In our reinforcement learning framework, we are gathering information about the dynamics by experience. So we interact with the system and we gather information about f. And we use this data to build some probabilistic models for the environment. We call this pi n. N stands for the time. So the more data I acquire, and then I will update my distribution pi n. Given a model pi n, I can compute an optimal control with respect to the data I know. So I based my decisions on my distribution, on my probabilistic model. So it will not be an optimal control, but it will be optimal with respect to my knowledge. And actually what the methods I presented before do is to minimize the average cost. They don't actually write it this way, but they do this. So we try to describe what these methods are doing. And the more experience I acquire, the better my model becomes. This is a hope. We can think that pi n plus 1 will be a better approximation of the true dynamics than pi n. And eventually, we want that pi n converges to the delta in f. Okay? We want that the more data I acquire, the better my model describes the true dynamics, and eventually it converges to a distribution which is the Dirac delta concentrated at the true dynamics f. The question we wanted to answer is the following. assume that my model gets more and more accurate. Is the optimal control u star pi n, which I find using my probabilistic model, getting closer and closer to the true optimal control? This means if pi n plus 1, if pi n converges to the delta, does the optimal control found by the model-based method converge to the true optimal control? And we can formalize these questions. So how far is v pi from v, where v pi is the one on the right-hand side, this here. So how far is v pi from v? And if I have a sequence pi n, is the sequence v pi n converging to v? And is the optimal control u star pi n converging to u star? These are the three questions. Okay, they are tough questions, and in particular the third one we try to answer. The first result is rather general, so deals with nonlinear systems, so f is nonlinear. We use the Wasserstein distance between probability distributions on a space of function, and these are some assumptions, Lipschitz continuity of the f and of the cost functions L and H. So we consider a sequence of probability distribution pi n, which is converging to another probability distribution pi infinity. You can think that pi infinity is the delta on a function f, is converging in the Wasserstein distance. The theorems we proved are the following. These estimates, this is an estimate of the distance between the value function pi n and the value function with respect to pi infinity. I didn't tell you that whenever we substitute the Dirac delta in problem B, we get a problem A. Okay, so there is this equivalence, and so here we can think the true value function V with respect to the true underlying problem, and here the value function that we can compute, because we cannot compute V. This is bounded by a constant times the distance, so it's a neat estimate, and whenever the distance goes to 0, also the value function converges. Then we try to answer the third question on the convergence of the optimal control, but on a simpler case, which is the linear quadratic control problem, where the dynamics is linear in both the state and control, and the cost is quadratic. We also assume that to know the matrix B, but the matrix A is unknown. So a probability distribution on the space of functions now becomes a probability distribution on a space of matrices A. Okay, so it is a finite dimensional distribution. It's much more common. And for instance, a Gaussian process becomes a Gaussian distribution on matrices. The cost functional is thus an average over matrices, over a space of matrices of the cost functional. And for this case, we prove that if pi n converges weakly star or equivalently in Wasserstein distance to the Dirac delta, say, in the true matrix A, we got a uniform convergence of the value function, a uniform convergence of the optimal control, and further, when pi n has a finite support, that this means pi is a finite sum of deltas, we can prove the convergence of the Riccati matrix. Don't know if you know, but the Riccati matrix is a matrix which solves the dynamic programming equation for the linear quadratic problem. And this gives the feedback form of the control. So we can conclude on our goal, which was the convergence of these methods. The question was, assume that my model gets more and more accurate. Is the optimal control I find using my model getting closer and closer to the optimal control? Well, in the LQR case, we proved yes. In fact, the optimal control is converging, and we are working in more general cases. And finally, some comparisons between the two fields. So let's say at the beginning that optimal control and reinforcement learning solve almost the same problem, but with different techniques. The first three, so continuous or discrete setting versus mostly discrete settings, and Markov decision processes. Okay, let's start from here. Optimal control assumes complete knowledge of the system, while reinforcement learning does not. Dynamic programming is one of the main approaches for optimal control, while in reinforcement learning most methods are based on dynamic programming, but they solve it approximately. And other comments, I added model-free reinforcement learning is direct adaptive optimal control, and probabilistic model-based reinforcement learning can be described through an optimal control problem with uncertain dynamics with an average cost. These are the main references. The first book is on optimal control. The second one is on dynamic programming and optimal control. These two are on reinforcement learning, and this is our paper on the RQR system. Thank you.
So, any other question for this guy? Come on. No, first. Just to change.
So you said that the more the experience, the better the results, more or less.
Yes.
So how much those applications are bounded to the problem that you are facing? Because I mean, do you actually can meet or encounter also overfitting or some problem of this kind?
Okay, so we use a trick here. We assumed that this assumption is satisfied. So we said, if pi n is converging to the delta, this is what happens. Now, in practice, there are needed other assumptions to guarantee, but we didn't consider it yet. But it's a good question.
Oh, okay. So Zambon was about to ask me something, I guess.
So I missed something about PN. So you start from an initial distribution, and then you update it with new information, or you don't consider any prior belief or something.
You can. There is a whole subclass of methods of Bayesian reinforcement learning, but yeah, I think it's not important what you start with, but rather what you are going to. Pilco, for instance, Pilco algorithm, they start with an initial distribution which is rather general, and then they use Bayesian regression on Gaussian processes. Okay. And so pi n stands for the distribution at time n.
Okay. So, any other question from the floor? No, I think we can go everyone to get a lunch. Well deserved lunch, indeed. And okay, so thank you.